Okay, hello and welcome to my channel. Today we're going to talk about stationary states in quantum mechanics, and these are considered the simple solutions for your Schrödinger equation. And the definition of stationary states is that they look kind of normal, and textbook definition is that it has a factorized factor of space and time, basically meaning that with a psi of x and t, you can write it as a psi of x and a g of t. So you can split your function that is dependent on x and t into two different functions that only depends on x and only depends on t. And with this, you put it back to your Schrodinger equation, you would get something like this. The gt part and derivative time, we take time part, and over here it is the energy part, and this has to be equal to an E, which is a constant with value of energy. So you put it into your Schrodinger equation and you would get something like this. So what you would want to do now is consider both of them independently of each other. So first, we're gonna consider the time part. So this part right here. We're gonna consider an IH bar dgt. This is dt, I'm sorry. T equal to energy party. So that, and I think you've seen this before. What you would get is an exponential function. I don't know what to call them, but yeah, you would get an exponential ce minus iet over h bar. This is what you would get. Next, we're gonna consider the space part. With the space part, you cannot really do much. You only write it as this psi of x as the time part. So you cannot really do that much transformation with the time part. It's just as is. Now you merge these two and into your double dependent function. You would get c psi of x, your time part. There we go. This is what you would get if you factor them out, consider them independently of each other, and then you merge them back into one big function that is both dependent on x and t. And a little bit of talk here with this c. Well, if you do the calculation, what you get is that c squared would equal to, I think, 1. Yeah, c squared is equal to 1. So when you sub it back, it's either plus or minus, which stands for odd or even, I think. So the c part is not really that important when you consider the normalizing of stuff when you square it. So let's just hop right into that. You want to normalize this, so this has to be equal to 1, right? Let's factor it out. Ex, this part would be star, that is iet h bar psi e minus iet h bar. Okay, we would command this to equal to 1. Okay, so as you can see, these two would cancel each other out. So those are gone. So what would you get ultimately is that the x of psi, only the x part is important for the normalization here. So when you want your psi of x and t to be normalized, you only need your space part to be normalized, since the time part would just cancel each other out. Okay, and I think that's it for today's video. Goodbye.